In this module, we are going to solve a couple of examples to illustrate how discrete time Fourier transform is computed and how it looks like. And for clarity, I have written down the discrete time Fourier transform equations as well as finite and infinite sum formulas that we will so frequently use in these examples. And please notice that notation wise, we are using capital X inside the brackets e raised to power j omega for the discrete time Fourier transform. And this notation differs from the one we previously used for the continuous time Fourier transform case. There we were using capital X and inside the brackets we were using j omega. So whenever you see capital X inside the brackets e raised to power j omega, it would mean we are talking about discrete time Fourier transform. Now our first example, we consider a one-sided real exponential decay function. Xn is a raised to power n un, and absolute value of a is less than 1. There can be two possibilities here. If the value of a is positive, that is between 0 and 1, the function will look like this. While if the value of a is negative, that is from -1 to 0, then there will be sign reversals whenever the value of n is odd. Now to compute the discrete time Fourier transform, all we need to do is to use the formula. So here we start by writing the discrete time Fourier transform formula. Xn e minus j omega n, and then we put the value of function here, n equal minus infinity to infinity. The function is an un e minus j omega n is already there. So this un will change the limits of this summation from 0 to infinity. So the limits of this summation are now from 0 to infinity an times e minus j omega n. In the next step, we can combine an e minus j omega n, a e minus j omega whole raised to power n, and the magnitude of a multiplied by e minus j omega, its magnitude is less than 1 because of this condition here. Therefore, we can apply the infinite sum formula. So we use infinite sum formula and we get the answer 1 divided by a 1 divided by 1 minus a e minus j omega. So this is the discrete time Fourier transform of the given function xn, and we can notice that this discrete time Fourier transform is a complex function in omega. So it has a real part, it has an imaginary part, and we can also express it in the magnitude and phase form. So quickly, if we write down the magnitude and phase of this function, the magnitude of this function turns out to be 1 divided by square root 1 plus a square minus 2a cos omega, and the phase of this function is tan inverse minus a sine omega divided by 1 minus a cos omega. So why I've written down the magnitude and phase, because here if we put omega equal to minus omega in this function, the magnitude turns out to be an even function of omega, because cos omega here is an even function. And the phase, if we find the angle at minus omega, then we will notice that the phase is an odd function. So phase is odd and the magnitude is even. And similarly, the real part of this function will be even function of omega, and the imaginary part is an odd function of omega. So we have conjugate symmetry, and this conjugate symmetry is from the fact that xn is a real function. And here are the plots of the magnitude and phase for both the cases when A is positive and when A is negative. Few things that we can quickly discuss. All these functions are periodic with period 2 pi. So all these functions are periodic with period 2 pi. This should be the case because the discrete time Fourier transform is periodic with period 2 pi. And symmetries are also obvious. The phase in both these cases is even, and the magnitude in both these cases is even, and the phase in both these cases is an odd function with respect to omega. Now, in the next example, we consider a discrete time rectangular pulse. And functional form xn is 1 if the absolute value of n is less than equal to capital N1, where this capital N1 is an integer and it is 0 otherwise. And here is an example of a rectangular pulse where the value of capital N1 is 2. Now to find the discrete time Fourier transform of this rectangular pulse, once again we use the discrete time Fourier transform formula. So the limits will now go from minus n1 to plus n1, and the function is 1 between these values, e minus j omega n. And here we can find the answer by using finite sum formula. For that, we will do a change of variable. Let k equal n plus n1, so that when n is equal to minus n1, k is 0, and when n is equal to plus n1, then k is equal to 2 times n1. And from here we have n equal k minus n1. So with this change of variable, x e j omega will be summation k equals 0 to 2n1 e minus j omega, and n is k minus n1. So we get e j omega n1 summation k equals 0 to 2n1 e minus j omega k. And we can now use the finite sum formula. So we use finite sum formula to get the discrete time Fourier transform e j omega n1 and 1 minus raised to power minus e j omega 2n1 plus 1 divided by 1 minus e minus j omega. So here we have the discrete time Fourier transform of the rectangular pulse, and we can bring it into the sinc form I will directly write the answer sine omega n1 plus half divided by sine omega divided by 2. So you can revisit the discrete time periodic square wave example in chapter 3 to see how we can get this form of discrete time Fourier transform. And here we have a plot of the discrete time Fourier transform. We have plotted this for n1 equal to 2. Once again, we can notice that discrete time Fourier transform is periodic with period 2 pi, and the discrete time Fourier transform of discrete time rectangular pulse is a sinc function. Okay, and this is the counterpart of what we saw for the continuous time Fourier transform of continuous time rectangular pulse. The Fourier transform of a continuous time rectangular pulse was a sinc function, but that sinc function was aperiodic. Here, when we have a discrete time rectangular pulse, its Fourier transform, discrete time Fourier transform is a sinc which is periodic, and the period is 2 pi. Now, the value of this function, at omega equal to 0, so x e j at omega equal to 0 is 2n1 plus 1, and we can find this value using L'Hopital rule. So in this case, the value of n1 is 2. Therefore, the value of this function at omega is equal to 0 is 5. And zero crossings of this function, zero crossings of this thing at 2 pi m divided by 2n1 plus 1. So in this example, the zero crossings are at 2 pi divided by 5, and this zero crossing is at 4 pi divided by 5, and so on.